Hello everyone, I'm Takayuki Kusumi from Okayama University, Japan. I'm glad to talk to you. Now, I will talk about 6-phase switched reluctance motors with small torque ripple, radial force ripple, DC current ripple, copper loss, and number of switches. So, let me explain the background. Recently, electric vehicles are widely used. For the EV application, interior permanent magnet synchronous motors are widely used because of its high efficiency. This high efficiency is caused by the permanent magnet inside the motor. However, the permanent magnet causes drawbacks too. For the low-cost EVs, such as personal small vehicles, the interior permanent magnet synchronous motors are expensive. Therefore, the low-cost motors which do not contain any permanent magnet are required. Then, the switched reluctance motors are expected. The switched reluctance motors does not contain any permanent magnet, so switched reluctance motors are low cost. Furthermore, the switched reluctance motors have robust structure. Therefore, the switched reluctance motors are attractive for the EV applications. However, the switched reluctance motors also have difficulties. In this slide, I explain the difficulties of the switched reluctance motors. This figure presents the switched reluctance motor driving system. And these waveforms present the phase current, the DC current, the torque, and the radial force applied to the stator. The horizontal axis shows the electrical angle. The switched reluctance motors are often driven by the square phase current waveform like this, because the copper loss is small. However, this square phase current waveform generates three types of large ripples. First, the DC current ripple is generated. This ripple flows into the battery and deteriorates the battery lifespan. Second and third are torque ripple and radial force ripple. These ripples generate large acoustic noise. Therefore, EV application of the switched reluctance motor suffer from these three ripples. Of course, many techniques have been reported to address those three ripples, so I introduce some of them. First is the tuning of the square phase current waveform. For example, on angle and off angle are tuned to minimize the torque ripple. As a result, the small torque ripple and small copper loss is achieved. However, this technique is not sufficient because the DC current ripple and radial force ripples are large. Second is the optimization of the whole phase current waveform. This method defines the phase current waveform like Fourier series and optimizes the Fourier coefficients to minimize the torque ripple and radial force ripple. As a result, the small torque ripple and radial force ripple are achieved. However, this method is not sufficient because large copper loss and DC current ripple are generated. Third is the simultaneous optimization of the phase current waveform and rotor shape. This technique is effective to achieve the small torque ripple, DC current ripple, and copper loss. However, this technique is also insufficient because the radial force ripple is not small. Consequently, the previous techniques suffer from the trade-off relation among the three ripples and the copper loss. However, to address this issue, a study has been reported. This previous study has optimized the phase current waveform for 5-phase switched reluctance motor to minimize the torque ripple, radial force ripple, DC current ripple, and the copper loss. In the case of the 5-phase, we can limit the phase current only this region. In this region, the negative torque is not generated. Therefore, the small copper loss can be achieved. And in this region, 3 phases are always excited. Therefore, 3 ripples can be suppressed. Therefore, the previous study is effective to the small ripples and small copper loss. However, the 5-phase switched reluctance motors require many switches in the inverter. Therefore, the purpose of this study is to achieve small torque ripple, radial force ripple, DC current ripple, copper loss, and the number of switches. To achieve this purpose, we introduce this approach. First, we replace the conventional H-bridge inverter with another inverter named N+2 inverter. As a result, the number of switches is reduced. Second, we adopt 6-phase switched reluctance motor rather than 5-phase switched reluctance motor. Because the 6-phase switched reluctance motor is suitable for the N+2 inverter, and the copper loss is further reduced. Third, we optimize the phase current waveform. As a result, the ripples are suppressed. From the next slide, I explain the approach in order. First, I explain the N+2 inverter. These figures present the conventional H-bridge inverter and N+2 inverter. In the conventional H-bridge inverter, the inverter consists of H-bridge of phase A, B, C. Therefore, 4 switches are required for one winding. On the other hand, in the N+2 inverter, the inverter consists of half-bridge of phase A, B, C, and one middle leg. Therefore, 2 switches are required for one winding, and 2 switches are required independent of the phase number. Therefore, the number of the switches can be reduced almost in half. And in addition, for example, the phase current of phase A is separated into the other phases and middle leg. Therefore, the N+2 inverter can apply arbitrary phase current waveform by applying appropriate current to the middle leg as this current. Next, I explain the adapting of the 6-phase switched reluctance motor. This figure shows the N+2 inverter of 5-phase switched reluctance motor and 6-phase switched reluctance motor. In principle, the 5-phase switched reluctance motor is preferable because the number of the switch is smaller than that of 6-phase switched reluctance motor. However, in the practical application, we have to consider the inverter loss. The current flows through the middle leg is calculated by this equation. In the 5-phase, the DC bias remains. Therefore, the large loss is generated at the middle leg. On the other hand, the DC bias is cancelled in the 6-phase switched reluctance motor. Therefore, the loss at the middle leg is very small. Therefore, the 6-phase is suitable for the practical application. Next, I explain the optimization of phase current waveform. the phase current waveform is expressed based on the previous study. The phase current is defined like Fourier series like this. In this equation, J0, Jn, Kn are arbitrary parameters, so the phase current waveform is optimized by the determination of these parameters. Then, we optimize the phase current waveform. The parameters of J0, Jn, Kn are optimized to minimize the evaluation function. This evaluation function presents the torque ripple, radial force ripple, DC current ripple, and root mean square value of the phase current. So, in the next slide, I show the simulation. From this slide, I present the simulation. The purpose of the simulation is to verify small torque ripple, radial force ripple, DC current ripple, copper loss, and number of switches. For this simulation, two types of inverters are used. One is the H-bridge inverter with square phase current waveform. The other is the N+2 inverter with the optimized phase current waveform. In this simulation, the switch reluctance motor has these characteristics. These figures show the inductance and radial force characteristic. In addition, the switch reluctance motor is driven by three types of phase current waveforms. First and second are the square phase current waveforms by the H-bridge inverter. The orange waveform was tuned to achieve small 3 ripples. The green waveform was tuned to minimize only the copper loss. And the blue optimized phase current waveform is applied by N+2 inverter. The pink current waveform flows into the middle leg of the N+2 inverter. Finally, the inverters are operated to apply these current waveforms by the hysteresis control. In the next slide, I present the simulation result. This slide presents the simulation result. This figure shows the phase current waveforms, torque waveforms, the DC current waveforms, the radial force waveforms, respectively. The horizontal axis shows the electrical angle. The green waveforms present the result of the square phase current to minimize the copper loss. The orange waveforms present the result of the square phase current waveform tuned to reduce 3 ripples. The blue waveforms present the result of the optimized phase current waveforms for the N+2 inverter. As for the phase current waveforms, certainly the root mean square value of the blue waveform is larger than that of green waveforms, but it is smaller than that of orange waveform. This result implies that the optimized phase current waveform achieved small copper loss, like square phase current waveform. As for the torque waveform, radial force waveform, and DC current waveform, the ripple ratios of the blue waveform is smallest. This result implies that the optimized phase current waveform achieved the small ripples. Consequently, this simulation supported that the small torque ripple, radial force ripple, DC current ripple, copper loss, and the number of the switches. Finally, I show the summary and conclusions. The switched reluctance motors suffer from a trade-off relation among torque ripple, radial force ripple, DC current ripple, copper loss, and number of switches. So, the purpose of this study is to achieve the small ripples, copper loss, and number of switches. To achieve this purpose, these approaches are introduced. First, N+2 inverter topology was adapted. Second, 6-phase switched reluctance motor was adapted. Third, phase current waveform was optimized. Then, the simulation supported the small ripples, kappa loss, and number of switches. That's all of my presentation. Thank you for watching.